undergrad.
I'm working with Centil now. We wrote a paper a few years back, and now we're writing another paper. As you mentioned it, yeah, we are kind of very similar. We fight all the time, and yeah, no, we were kind of on the same wavelength. And there's a former student of his who was a postdoc, who's part of the collaboration. He told me about that. There's a
Hello. No, I think. All right. Hello. Hello, everyone. Welcome to this very special lecture, the ICTS Sarojini Damodaran Fellowship public lecture. And I want to welcome all the students who've come from different colleges. I believe St. Joseph's, Christ, Mahalakshmi Ammal, and many others. So if you have not been here to ICTS before, welcome. We host a lot of public events, public lectures. Some of you may have come for some of them earlier. We even had one at Christ some last month. So ICTS is a research institute in the physical and mathematical sciences. We also have a lot of workshops in various research areas, which means a lot of visitors come through ICTS, and we do a lot of outreach activities. So public lectures like this are one of them. But we also have the monthly Copy with Curiosity at the planetarium. How many of you have heard of Copy with Curiosity? Okay, a decent fraction, but I think we could do better. So we should really be publicizing our Copy with Curiosity. It's held on a Sunday afternoon every month, one of the Sundays. We have this event at the planetarium in the city, so it's even easier to get to than to ICTS. So I hope many of you will join in for that. I think the next Copy with Curiosity, if I'm not mistaken, is being given by Spenta, I think, Spenta Wadia from ICTS itself, and I'm sure it'll be a fascinating talk. But today I'm very happy to welcome Professor Nathan Seiberg from the Institute for Advanced Study at Princeton, and as part of the Sarojini Damodaran Fellowship, And I'd like to thank the Shibulal Philanthropy Initiative for making this possible, making the visit of Professor Seiberg to India possible, and he's given a public lecture in TIFR Mumbai, and this is the second lecture as part of this fellowship. And so let me just, it's my privilege and pleasure to introduce Nati to all of you. Nati is one of the world's leading theoretical physicists and has made a dizzying array of contributions in multiple areas. Nati did his undergraduation in Tel Aviv, I believe, and then PhD at Weizmann before moving to the Institute for Advanced Study as a member, and he has held positions also at the Weizmann Institute and Rutgers University before moving permanently to the institute in 1997 as a permanent faculty member, and he has been there ever since. And Professor Seiberg's work, Nati's work, is something that is now sort of in the textbooks of people who study quantum field theory and related topics, and so some of the most spectacular developments in string theory and quantum field theory in the mid-90s was sparked off by Nati's work on what's now called Seiberg dualities, and also the Seiberg-Witten dualities for class of quantum field theories, and which was one of the first times one got sort of a deep understanding of what strongly interacting quantum field theories do. And this built on a lot of earlier work as well, in fact, from his postdoctoral days with Affleck and Dine and other works in the early days of string theory and so on. I won't have time to sort of list out all the various areas. I'll just mention some in non-commutative field theory, where I had also the privilege of working with Nati on one of the developments that arose from his work, the Seiberg-Witten theory of non-commutative gauge theories, and more recently, Nati has actually been interested in condensed matter systems, and I think his talk today will sort of pull together both these different aspects, the high energy aspects, which typically look at short distances, and the and what condensed matter physicists who like to study things at much lower energies study. And I think the unity of theoretical physics is something I think that has been a theme in Nati's work. Ideas from ideas which are universal and have sort of very wide applicability. And so, of course, for all these seminal contributions, Nati has had many recognitions. I'll probably name the MacArthur Fellowship. There is the Danny Heinemann Prize, the Dirac Medal of the ICTP, and also the inaugural Breakthrough Prize, now what's called the Breakthrough Prize, and many others, and which I'm sure, again, be a long list, which I don't want to bore you with, but he's also a fellow of the National Academy of Sciences and the American Association for the Advancement of Arts and Sciences. So, with all this, let me invite Nati over to tell you what happens at shorter distances. So, Nati.
Thank you, Rajesh. Can you hear me? Oh, it's almost a full house. I'm very happy to see that. I'm especially happy to see the young people in the audience who are interested in science. I hope this talk will not deter you from following your interest in science. This is my third visit to ICTP here, fourth time in India. Sorry? ICT up. He said ICTP because ICTS, sorry about that. Um, and I love it here. India is a physics powerhouse, and the physicists here are among the best in the world. And it's a lot of fun and pleasure to come here and interact with them, listen to hear what they do, and learn from that. It's extremely stimulating. Turning to the talk, the title of the talk is a question. What happens at shorter distances? And I will address that. I will give some answers. But the main theme of the talk will be to discuss the meaning of the question itself. Why do we ask this question? What does this question mean? And toward the end, we could even address the question, maybe it doesn't mean anything. So let's get to work. It's common in science, but also in everyday life and in all branches of science, that we have different disciplines that address problems or issues at different length scales. And let me give an example from everyday life. This is an engine of a car. The engine was designed by engineers, and when it breaks, mechanics fix it. And the engine is in the car, and here is the bigger object, the car itself, and there's a driver in the car. And the driver drives the car, and the driver needs to know how to keep the car in the lane, how to manipulate it in traffic, and so forth. Most people who drive cars have no idea how the engine works. That's just a fact. And in fact, the people who design the engine, the engineers, might not even have a driver license. So one can specialize in one activity and be very good at it without needing to know all the details of what happens at longer distances, the structure of the car, or conversely, all the details at shorter distances. Let's move to longer distances, and this is some highway, and it has bridges and many roads at different heights, and they go on top of each other. And the people who design it are urban planners and also civil engineers. And they have to know how many lanes we need, how much traffic there will be, how high it should be, how strong, etc. They don't have to have a driver license. You can be a very good civil engineer without knowing how to drive the car. Nor do they have to be mechanics who can fix the engine of the car. Conversely, the people who work at shorter distances, the mechanic on the car or the driver, have no idea how to design such a bridge. And this is actually a theme, and we'll have a lot of it in this talk. And I will always keep this pattern that the shorter distances are at the top, and as we go down the slide, it will always go into longer and longer distances. And the main point here is that we have expertise that are needed, which are kind of distinct, and you can be an expert in one of them without knowing all the details of the other. And at the same time, there is a relation between what's going on at the different layers. Let me give another example of it, something that we've all experienced over the last few years, and this is the pandemic, COVID-19. And again, we'll have things at shorter distances, things in medium distances, and at longer distances. At short distances, we have the virus. It's very small, 20 to 500 nanometers. In scientific notations, it's 10 to the minus 7 of a meter. The people who study it are virologists. They study the structure of the virus, its RNA, and they design vaccines. We are still allowed to use the word vaccines. This might change in the future. And they design vaccines that would target the virus. And okay, that's what they do for a living. At longer distances, we have epidemiologists, people who study public health. They address questions like, when we have the pandemic and at the peak, should we or should we not wear masks? Are the masks helpful? How far apart from one another should we be? I remember it was about 2 meters at the time. Then they changed their rules about that. And again, most of the people who design these rules, who put forward these rules, don't know the structure of the virus, and it doesn't matter. And the virologists who study the virus might not know about the relations between people, how far one could be from each other. And as we go to longer distances, people wanted to stop the spread of the pandemic. And then the questions of, should should we close the borders? Should we isolate people who come from other countries? And these are very interesting questions involving politics, foreign relations, and the scale that's involved is completely different. We had 20 to 500 nanometers at short distances. We have 2 meters, maybe 1 to 10 meters here. And here we have hundreds and thousands of kilometers. Vastly different distances. There is relation between the different disciplines, but one can specialize in one without paying too much attention to the other. This is actually extremely common. In most of science, in fact, everyday life follows this pattern that we have distinct disciplines at different length scales. It's actually quite interesting that nature has such a hierarchical structure, that phenomena at one length scale are independent of most of the details at the other length scales. We can specialize on one thing, ignoring completely the other. There is no need to understand simultaneously all the details at all scales. We study nature one scale at a time. This is actually quite remarkable. I do not know why this is the case. It didn't have to be the case. It could have been that everything is much more complicated and you need to understand what happens at short distances and at long distances at the same time. That's not the case. If that had been the case, it would have been impossible to understand nature, because we would have to understand what happens at the shortest distances, atoms, molecules, and we'll talk more about them later in the talk. And at the same time, we'd have to be experts in the study of the universe as a whole, cosmology, geophysics, and so forth. Fortunately, that's not the case. We can say that nature is kind to us. It didn't have to be so simple, but we are fortunate that it is simple. We are fortunate that we have this separation of scales and we can study nature one scale at a time rather than addressing all these complicated problems at the same time. Einstein famously said about that subtle is the Lord, but malicious he is not. The laws of nature are subtle and interesting and complicated, but we have a chance of understanding it. And one reason we have the chance of understanding it is that we have this phenomenon that the problem breaks down. Let me give another example of that, which will also be important later in the talk. And this is the subject of hydrodynamics. Hydro means water, and the Greek word dynamics means power or force. And this is something that has been studied for centuries. The name hydrodynamics first appeared in the late 1700s. And the name discusses the flow of water, but in fact, exactly the same thing is for all fluids. People these days also study it in the context of fluid dynamics. And also for the flow of air. By the end of the 19th century, there was a rather detailed description of the flow of water. The equations that govern the flow of the water were found by the end of the 19th century, and they work extremely well. Yet, they are still a very active line of research for mathematicians. Mathematicians want to prove properties of these equations. This is a very exciting field. But there are also physicists working on it, addressing various questions about these equations. And also engineers who design airplanes or cars. They want to make sure that there isn't too much drag on the car. And in order to do that, they need to understand the flow of water or air. We look at this picture, we see here the water, the shape of the water, and these equations control how waves appear on the water. And so we have water underneath the surface, and we have air on top. And there's kind of a two-dimensional surface of the water, and as the water flows, this surface also moves. And we have swell, and people do all sorts of fun things with these waves. But this picture is not quite right. It's not quite right because if you look at the surface of the water with a microscope, with a very powerful microscope, there is no shape for the surface of the water. Instead, what we have there is molecules. So in here, in the water, we have a lot of molecules bouncing around, flowing if the whole direction of the water flows to the right. Most of them move to the right, but some of them actually move to the left. Some of them move up, some of them move down, then they collide with each other and they move, and it's extremely complicated. The same is true for the air molecules in here. So we have oxygen and nitrogen and many other things, and there are all the molecules here. And again, it's extremely complicated because they have so many molecules and they move in all these directions. In fact, if we look very closely and we get close to the surface of the water, there is no surface there. The fact that there's a surface there is an approximation, is an illusion, because we have more water molecules here and more, say, oxygen and nitrogen molecules here, but there is no clear separation between them, because water molecules can go up to the air and air molecules can get into the water. And if we look at it, here's one molecule, here's another molecule over here, and the surface that separates them is mathematical surface. There's nothing there. And we can't even say that it is in one place or another. So the surface is not really there, but it is a very useful concept. It's a very useful approximate concept. If we wanted to give a description of the water that is used for engineering and so forth, we'll use the same equations of the 19th century, and they work extremely well. But this description is not complete. A more complete description involves these lots and lots of molecules. Every one of them moves around in different directions. And if we wanted to give a complete description of what's going on here, we have to keep track of all these 10 to whatever number of molecules, astronomical number of molecules, and solve complicated equations how they move and bounce around. And it will be totally, totally useless. So it will have to be a lot of work, which we don't really need because we don't care about most of this information. If we would like to know how high the waves will be, we need to understand these equations of the 19th century. And at that time, people didn't even know that they are molecules. So we'll see this separation of scales with different description at different length scales. And the description at longer distances is kind of an approximation, but a very effective approximation. And I'll say more about that soon. In philosophy, this separation of scales and going to shorter distances to find the more complete theory is known as reductionism. It's describing complex phenomena in terms of the fundamental constituents. And over the past centuries, research has progressed in a two-way approach. On one hand, we went into matter to understand deeper and deeper rules at shorter and shorter distances. It's like peeling an onion. And every time we peel a layer, we find inside deeper truth, more correct theory at shorter distances. For example, of the water, first people understood how the water flows. And then at shorter distances, we have molecules, which give us a more complete description, a more accurate description. But the old description with these equations that describe the smooth flow of water is still interesting and it's still valid. So one direction is going inwards to shorter distances to find deeper and deeper laws of nature. And I'll say more about that soon. In the opposite direction, people use the known laws of nature, trying to derive new phenomena at longer distances. So we have this two-way approach, this two-way street. On one hand, we try to find deeper and deeper rules at shorter and shorter distances. And on the other hand, we try to use these simple rules and go to longer distances and find new phenomena. And we need to do that for two reasons. First, to make sure that the equations that we found, the rules of nature that we found are indeed correct, but also to find new phenomena. And I'll soon give an example of that. So we refer to this effective description at long distances. This description at long distances is an effective description. It's approximate, but very effective, very useful. And progress happens in the two directions. First, we try to find the long distance theory. We use it to find clues to what happens at short distances. This is this two-way approach I talked about. We use it, we looked at all sorts of phenomena. We try to understand what underlies them. What are the more basic rules at shorter distances? At the same time, we explore more and more the new phenomena at short distances and try to understand them better and better. We also move in the opposite direction. As I said before, this is a two-way approach. The long-distance theory is used to derive long-distance phenomena, both to find tests of this phenomena and to understand new phenomena. So, for me, this is the beauty of science. We have simple underlying laws. The laws of nature are relatively simple. They could have been much more complicated. And yet, they can lead to very rich and complicated consequences. The fact that we have biology and a lot of different people who look differently, a lot of materials with different properties, this is a sign of the richness that come out, and they all come from relatively simple equations at short distances. Now, these two lines of research, going inwards to find the simple underlying laws and going outwards to find the complicated consequences, are not independent, and some people do one or the other, and there's an interesting interplay between them. And to make it even more interesting, there are also, of course, technological applications that come out of it. So we are really in a very happy situation where we try to find deeper laws at shorter distances, interesting consequences of them at longer distances, and along the side, we build a computer or build some other device, we go to the moon, etc. So let me get into more details with some existing disciplines. And I'll talk about condensed matter physics or chemistry, and I could even add here material science. And again, we should, whenever we study such things, the first thing to know is which length scale are we talking about? So when you study phenomena in physics, especially, but also in other branches of science, the first thing is what length scale are we talking about? So at short distances, in these disciplines of condensed matter physics or chemistry or material science, we have atoms, and the atoms are about 10 to the minus 10 meter. That's a small atom, then they are bigger atoms. They have a nucleus at the center with protons and neutrons, and there are electrons that circle around them. And we more or less understand the rules of how these atoms work. They're subject to the rules of quantum mechanics that was understood early in the 20th century. And out of these rules and out of these atoms, a huge number of materials come out at long distances. And it's extremely interesting to see how different materials can arise out of the same basic building blocks. Very, very rich spectrum of materials we can find. Some of them are soft, some of them are hard. They have different colors. They might conduct electricity or not. They might be magnets or not. And they have all sorts of new phenomena, new properties. And this is an active line of research, and people still find new kinds of materials these days. And these new kind of materials are being used to build new devices. There are all sorts of ideas how to find new memories for computers. This is a very, very useful subject done by chemists, condensed matter physicists, material science, etc. So this is one line of work, condensed matter physicists going from atoms to materials in everyday life. This is another discipline, high energy physics. Here we study the basic building blocks of nature, what kind of matter we have, what is matter made of, what are the forces that act on the elementary particles. And we have a wonderful model known as the Standard Model of Particle Physics, and it describes the basic particles. These are electrons, quarks, maybe you heard of photons, the Higgs particle that was in the news, and it operates at distances larger than 10 to the minus 18 meters. This is quite remarkable that mankind understand what happens at these shorter distances with enormous accuracy. We have a very detailed picture of it. So recall we talked about atoms that are 8 orders of magnitude bigger than the laws of particle physics. And indeed, we have a rather good understanding of everything that happens between distances of 10 to the minus 18 meters, where we have electrons, particles called quarks, and many others, all the way up to 10 to the minus 10 meters. So again, this is the short distance phenomenon, and this is the long distance phenomenon that comes from it. And the laws of physics at this scale imply the laws of physics here. And on the previous slide, I took that as the starting point. That was the short distance phenomenon. And out of it, we had various materials at longer distances, at everyday life. So this is another example of this hierarchical structure that on one hand, we try to go from here to here. That was done during the 20th century, was mostly the second half of the 20th century. And we're still going from here to here to understand more properties of atoms, etc. And we also have this other layer from here to the materials around us. So this thing begs the question, what's higher up here? If this is an approximate description of our understanding here, what is the understanding at shorter distances for which this is our approximate description? So we could imagine that just as we had this hierarchical structure before, this can continue. And as we go to explore nature at shorter and shorter distances, we are going to uncover new rules that would make the old phenomena, like what we see here, would be kind of an approximation, just as the story of the atoms is an approximation to deeper truth occurring here. And the answer to this question is that we don't know. One of the challenges in physics today is to understand what happens at shorter distances. What happens at 10 to the minus 18 in smaller distances? So we don't know the answer to that. And in order to address that question, we need a microscope, a more powerful microscope that will allow us to look at shorter and shorter distances. And these microscopes are called accelerators or collider. This is a picture from the strongest accelerator we have today. It's called the Large Hadron Collider. It is in the laboratory called CERN outside Geneva. And people talk about today about building a future collider, a future experiment that will perform experiment at higher energies and will give us a glimpse of what happens at even shorter distances. The other way to make progress is to recall that whenever we have a description at one length scale, it's always approximate, because a description at shorter length scales is more accurate. We talked about that before in the example of the water. The true description is in terms of the molecules. So the same could be true here, and the standard model of particle physics is only an approximation to a much more complete and more interesting and more detailed story. How can we test it? How can we find it? We can find it by performing precision measurements at large distances. So we should either go to short distances with a more powerful microscope, or stay at the same distances but measure things more accurately. And there's a lot of activity to measure the same quantities more and more accurately, with more and more significant digits. So let me summarize the disciplines that I talked about so far and compare condensed matter physics and high energy physics. So at everyday life, we have various materials, and the primary goal of condensed matter physics is to find new phenomena by using the known rules of nature at distances larger than 10 to the minus 10 meters. So most of the people in condensed matter physics and chemistry and material science and others work in the physics of going outward. So we know the laws of nature that give us atoms. We know about quantum mechanics, atoms, molecules, and all that. What kind of materials can we construct out of them? And these are the materials. High energy physicists have the opposite goal. We understand what's going on at 10 to the minus 18 meters, and our goal is to go downwards or inwards into matter and find deeper rules at shorter and shorter distances. Surprisingly, these two distinct disciplines use very mathematical language, which is again very surprising and very fortunate. It didn't have to be the case that the same mathematical language is used for both. In this context, I found a good quote by Steve Weinberg. Steve Weinberg was one of the greatest physicists of the 20th century. He was one of the architects of the standard model of particle physics that I just talked about, the one that describes electrons, particles called quarks, and all the forces that act between them. There's the strong nuclear force, the weak nuclear force, etc. Unfortunately, he died a few years ago in July of 21. And in his talk he gave in January 21, a few months before his death, he said that there's a school of philosophy of science associated in particular with the name of Thomas Kuhn that sees the development of science, particularly of physics, as a series of paradigm shifts in which one point of view our point of view changes so radically that we can barely understand theories of the earlier times. He's basically talking about this hierarchical structure that I talked about, where we have some understanding at one length scale, it is approximate, and then there's huge progress, and we find deeper truth at shorter distances, and then we can throw away the old theory at long distances because we don't need it, because we just go inward to find deeper and deeper truth. So this is the Thomas Kuhn school of thought. But then Weinberg continues and says, I don't believe it for a minute. I think that our successful theories always survive as Newtonian mechanics has, and as I'm sure the standard model will survive, by that he means the standard model of particle physics, will survive as approximations. So these approximations are still very useful and very good. So when I talked earlier about these equations of the 19th century that control the flow of water, the equations are still useful today. They are not obsolete and they are not being replaced by a deeper truth at short distances. So we have separate descriptions of nature at different length scales. All of them are useful, even when they are incomplete. So let me summarize what we've seen so far, get kind of a map of it. We talked about various length scales. We talked about particle physics at 10 to the minus 18 meters. Out of it, we can derive at longer distances the atoms and molecules, 10 to the minus 10 meters. And out of these going to longer distances, we have all the matter around us. We talked about various materials, and we also talked about waves in the ocean that comes about from the motion of these molecules. And we can also move in the opposite direction to shorter distances here. So we don't know the answer here. We do not know what happens at shorter distances, but we could try and be very ambitious and go to extremely short distances, much shorter than this 10 to the minus 18 meters, and that is at 10 to the minus 35 meters. So this is really very far. It's extremely short, but it's extremely interesting, because this is where we face the biggest conceptual question in physics. In physics, we learned in the 20th century of quantum mechanics that replaced Newton's theory of the mechanics of the motion of bodies. And we also learned by Einstein that gravity is described by his theory of relativity. So we should combine both quantum mechanics and relativity. And we could immediately ask ourselves, at what length scale does this thing happen? Because as I told you again and again in this talk, when you talk about something in physics, the first thing to know is at what length scale are we talking about? And this question was addressed for the first time by Max Planck. And interestingly, he addressed this question in 1899. And he said that this is the length scale we are interested in, 10 to the minus 35 meters, or in terms of time, it's 10 to the minus 43 seconds, tiny fraction of a second. This intellectual achievement of Max Planck is really absolutely remarkable, because he knew at what length scale all these phenomena will be important, what is the basic laws, what is the basic scale of physics. He knew it in 1899. And it is remarkable because in 1899, people did not even know that there are atoms and they did not know their structure. They did not know about quantum mechanics and did not know about general relativity. All these things came later, decades later. Still, Max Planck knew that at this length scale, something special happens. It's quite remarkable how somebody could do a calculation and say where it happens without knowing any of the ingredients that lead to it. So we should address the structure of the universe at length scales of 10 to the minus 35 meters, or a time scale of 10 to the minus 43 seconds. I'll have more to say about from this point on till the rest of the talk. I'll talk about these distances. But the main point understanding here, which shows how deep and important it is that if we understand the physics of 10 to the minus 43 seconds, we'll understand the origin of the universe. We'll understand creation. Creation is understanding physics at 10 to the minus 43 seconds. And why this is so, I'll say in a lot more detail. So how should we think about it? How should we think about these phenomena at tiny distances? Experiment is not a good guide, because we have difficulties at 10 to the minus 18 meters, and we are trying to push maybe one order of magnitude 10 to the minus 19 or 20, and that's already very, very difficult. This is much more ambitious. We try to go to 10 to the minus 35. How should we think about it? Well, it's a big problem, and we don't have experimental clue, but we have various ideas, and the leading idea is known as string theory. So string theory is an ambitious attempt to give a comprehensive description of nature. It should explain all the elementary particles. We talked about electrons, photons, quarks, Higgs boson, etc. all of them should be derived as an effective description, as an approximate description out of a more fundamental theory, and that theory is string theory. It should also explain all the forces of nature, like electromagnetism or the strong nuclear force and very reactive decays. And Einstein's theory of relativity is a theory of space and time. It addresses the structure of space and the meaning of time. All that will also come out of string theory. So this is a very ambitious goal. There's been a lot of activity, a lot of progress, but there are enormous challenges. First, we don't yet know the answer. And that's why I'm so happy to see young people in the audience, young people who are interested in physics. Some of them will come and will solve this problem, and that would really be fantastic. This will be an achievement that will be remembered for centuries. I really encourage you to go and do study physics because it's really exciting. So we don't yet know the fundamental formulation of the theory. We do not know what the basic principles are, what the basic equations are. We can do a lot of calculations, but we don't really know what's going on there. It's actually quite strange that we could do anything. And as I said, we do not have any direct experimental confirmation. And that's bad two ways. First, it doesn't tell us that we are really on the right track. And second, it doesn't give us clues. In the past, experiment gives us clues how to move forward, how to find these better laws, the more fundamental laws at shorter distances. We don't have this guidance. Yet it is extremely promising. It is extremely promising because this theory has all the necessary ingredients to describe nature. It automatically has quantum mechanics. Quantum mechanics is not an option here. It comes as a package deal with the whole thing. It automatically includes gravity. So it's not that we have a challenge, how are we going to combine gravity with quantum mechanics? In fact, both quantum mechanics and gravity are inevitable here. And it also has forces and particles of the kind we observe in nature. Not in a lot of detail, but they do look the same. So that looks extremely promising. Also, the theory has miraculous and surprising consistency. We perform calculations and miraculously things work out. It's quite clear that there's something very deep going on, something that we do not yet understand. And it satisfies the criteria for a deep intellectual structure because it leads to many surprising connections between different branches of physics and mathematics. Historically, the good developments in science were better than they were designed to do. People wanted to solve one problem, and in the course of doing that, they developed tools that addressed many other problems they didn't even know about at the time. For example, Newton wanted to understand how bodies move. Along the way, he invented calculus, which of course helped him understand how bodies moved, but the same calculus also addresses many other phenomena, and it's central in mathematics, central in other branches of physics, and even social scientists use calculus these days. Something very similar happens here. String theory, independently of addressing the question of finding the basic theory of nature, independently of trying to put together gravity and quantum mechanics, and there's a question of whether it does or does not describe reality, independently of all that, it has already influenced a lot of other branches of physics and inspired activities that could be measured, produced new phenomena, new predictions, both in condensed matter physics, in plasma physics, and elsewhere, and also has led to enormous impact on mathematics, completely changing some fields in mathematics. So that's, for me, this is the sign that something very deep is going on here. The theory is better than the questions we are trying to address with it. It does much better than that in a way that we do not yet fully understand. And these are these unexpected implications. So I could give a whole talk just about this aspect of it, but I would like to switch to a slightly different direction, also involving string theory, which will connect to the theme of the talk. So recall that the theme of the talk was the question, not so much the answer, the question of what happens at shorter distances. That's what I said at the beginning. We said we'll address what does the question mean. And we said two things. One, nature is broken into various disciplines are at different length scales. We can do it in this hierarchical structure. And there's an interplay between the different layers. As we go inwards, it's more and more fundamental. And as we go outward, we find rich phenomena. So related to that, we could ask, what does distance even mean? What does it mean to go to short distances? So the question I would ask is, what is space? Now, we all have some intuitive understanding of space. We have a ruler that measures distances in space, like the director is sitting here close to me, and the former director is sitting a little bit further away. And the younger people in the audience are even further away. So we all have this intuitive notion that something is to our left or to our right, up or down, forwards or backwards, etc. So this is an intuitive notion, and we can make it more precise using the ruler that measures distances. And we could use this microscope to see what's going on at shorter and shorter distances. Now, many string theorists believe that in the context of string theory, the notion of space will not end up being fundamental. So this is again the topic that I could give a whole lecture about. And what it means is that it is an emergent concept. So just as we go from one distance scale to another, the notions change, what we're talking about changes, etc. As we go deeper down in string theory, there would not be any space at all. The idea of space is some approximate notion that we see at long distances. So the notion of space is not fundamental, and it emerges as an approximate notion at long distances. And let me explain that using an analogy that I've already used in the talk earlier. And that is the waves of the ocean. So recall earlier in the talk, I talked about hydrodynamics, and I said that we have the surface of the water, and it is governed by some equations, these equations of the 19th century. And if we look very deep, so if we look from afar, the way you do, you see the surface of the water. It's like a two-dimensional curved surface. But if we look very close, we see that there is no surface here. Instead, we have all sorts of molecules bouncing around, and we have molecules of air bouncing around here. And even from here, I can see that there is no clear separation between them. There's some fuzzy region in between where there are some molecules of air and some molecules of water, and they're kind of around, and I can't say the surface that separates them is here or here. So the notion of the surface that separates them is an approximate notion. It seems to us that there is a surface, but if we look closely, there is no surface. So the surface of the water looks like a two-dimensional sheet, but if we look closer, there is no surface. It's only an approximate illusion. And we have an effective macroscopic theory controlling the shape of the surface. And this is hydrodynamics that I talked about before. So now we can draw an analogy. And this is the dictionary of the analogy. The surface of the water, which looks like a two-dimensional surface, and I said that's just, and it exists, and we look at it, it seems like it exists. This is analogous to the emergent space. So the space that we see around us, that the director is there and I'm here, that space is just an illusion. There is no such thing if we look closely enough. This distance between us is just an illusion. In hydrodynamics and these equations of the 19th century, in this analogy, are general relativity. So just as these equations are an approximation that tells us how the water flows and what the surface of the water looks like, while there isn't really an exact surface at all, the same is for general relativity. General relativity arises here as some kind of an approximate notion at long distances. And the water and air molecules that give us a more detailed description, they are like string theory. This is the true thing that happens at shorter distances. Now, we cannot prove that this is the case, but there are many situations where we can clearly see that this is indeed the case. And there are many examples of that in different places. And many string theorists, if not all, believe that this will actually end up being the case in the end. The notion of space will end up being emergent. So if this is the case, there are very interesting consequences that we get immediately. We say that the notion of space will break down at some distance. What distance? Well, there's only one distance in the problem. This is this Planck scale, 10 to the minus 35 meters. So that would mean that the notion of space will make no sense at shorter distances. There is no sense to ask what happens at shorter distances, because the notion of space and the notion of distance do not make sense there. We cannot ask ourselves, what are the laws of nature at shorter distances? I'll soon say more about that, but that's already quite interesting because the theme of this talk was that we have different disciplines at different length scales, and we can go inward to find deeper truth at shorter distances, but here we will stop. We cannot go to shorter distances for the simple reason that there are no shorter distances. So again, I said it earlier in the talk, the main thing will be to address the question rather than the answer. The notion of distance will cease to make sense at these short distances. Let me move to time. So what is time? So we all have some vague intuitive notion of time. And if for space we have an intuitive notion of space, here I was more tentative and I said, we have a vague intuitive notion because philosophers spend a lot of time asking what exactly do we mean by time, and also physicists don't quite understand what we mean by time. But intuitively we know. Some of you ask probably, when will this guy stop talking? So we know he's been talking for how long? Some 40 some minutes, and we have maybe a few more minutes till he ends. So we know what happens. We have this idea of things evolving in time. And physics is indeed about time evolution. We make predictions, and then we perform experiments to test the predictions. And the experiments are done later in order to test a prediction rather than before. This is known as causality. The cause is before the effect. So time is really built into our understanding of nature, and in fact of understanding of everything. You cannot go back and kill your grandfather. This is the famous grandfather paradox. And so time is there, and there's nothing we can do about it, and we wish we understood it better. However, in Einstein's theory of relativity, space and time mix together. And therefore, if space is emergent, maybe time is also emergent. And just as we said that space could be an emergent notion, some approximate thing that we see at long distances, but it's not there in the fundamental level of the theory, this suggests that maybe time itself is also not fundamental. And I put this slide through the hourglass to tell us that we can no longer use it. It only appears as an approximate notion at long distances. And therefore, it's meaningless to ask what happens to the universe before 10 to the minus 43 seconds. Because time doesn't exist before that. The universe appears at 10 to the minus, when it's 10 to the minus 43 seconds, and evolves from that, and we cannot ask what happens earlier. So understanding how time emerges will really explain what creation means. We cannot ask what happens before creation or what existed before creation, not because it didn't exist, but because even the question does not make sense. So if this is indeed the case, and space and time are indeed emergent, then we have an ultimate short distance and ultimate short time. And the notion of space and time and distance would cease to make sense there. Therefore, we can no longer ask what are the physics, what are the laws of nature at shorter distances? What are the laws of nature on time intervals shorter than 10 to the minus 43 seconds? We cannot ask because it doesn't mean anything. And if we cannot ask, we definitely cannot answer it. So if I said at the beginning of the talk, I posed the question, what happens at shorter distances? Here, we will not even be able to ask the question because it doesn't mean anything. So if we understand the laws of nature all the way down to this Planck scale, 10 to the minus 35 meters and 10 to the minus 43 seconds, this will be the end of this reductionist pursuit to find deeper truth at shorter distances. So for centuries, scientists tried to find the basic laws of nature. And at every layer, there was a deeper layer with deeper truth. If these ideas are true, and it might take a long time to find out, once we reach these distances, this will be the end. There will not be any deeper truth, and there will not be more fundamental physics. This would be the most fundamental physics at the shorter distances that there are. So let me summarize the talk. What have we seen? We started with the question, what happens at shorter distances? And the first thing which was important here was this separation of scales. That we have these different phenomena at different length scales, and they're kind of independent of each other. We can study one of them without understanding the others. And I gave examples of cars and virus, and example in hydrodynamics. And then I gave examples in chemistry, particle physics, and others. And that's actually extremely satisfying that nature is kind to us, that we can study it one scale at a time. And we go to shorter distances to find deeper truth. And using this deeper truth, we understand phenomena at long distances, and this is this reductionism that we talked about. So on one hand, it is simple in the sense that we can break it, and on the other hand, it allows us to go between different length scales using these reductionism ideas. Now, it didn't have to be so simple, and I really find it satisfying that it is simple, but also baffling or surprising. Why is it so simple? It didn't have to be like that, and we are really fortunate. And we talked about physics at different scales. First things we did not talk about at the largest scales. The longest scale that we can possibly discuss, we discuss cosmology. This is the universe as a whole. At somewhat shorter distances, we can discuss astrophysics, stars, and all sorts of other interesting objects in the sky. We can also discuss geophysics, earthquakes on Earth, and so forth. And there are many rich and interesting phenomena there. As we go to shorter distances, we talked about various materials around us, soft, hard, conduct electricity or not. And as we go to even shorter distances, we see quantum theory, atoms, and molecules. And we keep going inward to shorter distances, and we find the standard model of particle physics with its electrons, quarks, Higgs bosons, and others. And the next step, stop. We don't know. So this is something for the younger people in the audience to join the effort and find what happens at shorter distances here. And next, there's the more ambitious thing, even though we don't know what happens immediately after the scale of particle physics, going all the way down to quantum gravity and string theory and understand what happens at the ultimate shortest distances. So we talked a little bit about quantum gravity and string theory, and we put forward the suggestion that the idea of space, the notion of space, is an approximate notion, and it emerges from something else. We made an analogy with the waves of the ocean, with the surface of the ocean, where these waves is not really fundamental, is only approximate, and it doesn't really make sense if we look at it at very short distances, but it is still interesting. And if this turns out to be the case, this reductionism of going to shorter distances to find rules that give us insight of what happens back at longer distances, this will end. There will not be any deeper truth. And that's why I put this line through the microscope. We cannot continue to go inward. We can no longer ask what happens at short distances. And this will be the ultimate theory. Here we will find the final laws of nature. So this effort that has been going on for centuries, once we are there, this effort of going inward will reach an end, and this will be the ultimate theory. However, this will not be the end of science. It will not be the end of science because there will still be many new phenomena that come out of it. There will still be new materials, and there will still be new technology made out of the new materials. So we don't know how long it would take to get there. It might be some smart guy will figure it out tomorrow, or it might take even a century until this is understood, or maybe more. But I think it will be quite exciting to reach this point. So therefore, I'm going to stop now and thank you, and I'll be happy to answer questions if there are any.
Thank you very much, Nati, for hello. Let me thank Nati again for a characteristically lucid talk. I'm sure there are questions from people in the audience. We'll take some. Please put up your hand. Please keep the question on topic, so to say, and be brief with your articulation. Yes.
Sir, a small question regarding the concept of emergence, especially like you were talking in terms of like universe was brought on from a reductionist perspective, and then with respect to the concept of string theory and we got to conceptualize space as an emergent phenomena, and based on that we discretize laws for each and every length scale. So the question is like in terms of string theory, we have this landscape problem where we. Oh, sorry. Can I just continue from where it stops, sir?
I can hear without the microphone also.
Can you hear me now?
Yep,
Yeah. So,
even better. Yeah.
Sure. So the thing is, I was asking regarding the concept of emergence in terms of the length scales. So we were reductionizing in terms of the length scales previously, and then we, after realizing the concept of gravity in terms of like general relativity and you say quantum mechanics, we got to take the concept of universe as an emergent phenomena, and we got to just converge both of these phenomena, especially like in terms of you say the emergence and the reductionist phenomena. My question is like in terms of string theory, we have this problem of landscape problem, especially like how do we idealize these spaces in terms of the strings, or you say, or the space?
Did you say landscape?
Yeah, the landscape problem especially in string theory.
Okay, so first of all, landscape is not a problem.
Okay.
This is a phenomenon, this is a property of string theory, that it has many solutions. And it's common in science that we write one equation and the same equation can have many solutions.
Yes, sir.
If you studied quadratic equations, have you studied the quadratic equation?
Yes,
It
sir.
has two solutions.
Yes, yeah.
And more sophisticated equations have more solutions. And string theory is very rich, it has lots and lots of solutions. Now, is this good or bad? It's not a value judgment, it's just a fact. There are many solutions. Now,
Yes, it
is that something that will help us understand nature? I think the judge is still, the jury is still out on that. It's not yet clear whether this is a good thing or a bad thing, but it's a fact. So that's not a problem. Now, having said that, this is really unrelated to what I was talking about.
Yeah.
I was talking about the fact that there is this theory, there are these equations, we don't even understand what the equations are. And one consequence of that is that space will not make sense fundamentally, will not exist, but it will appear as an approximate notion. That's what I wanted to say. And this will be true with or without the landscape.
Yeah, it's was in the fundamental scale, yes.
Yeah, there was a question here, I think. Okay.
Hello. So you talked about reductionism. What about the opposite limit? Like, is there a limit to get larger and larger? Like, do we have any hints if there is a limit to that? Yeah.
Okay, so I did not talk about cosmology. Cosmology is a very interesting field. Could give another talk on that. I think I actually gave a talk about that here a few years ago in Bangalore. And I think you were the host actually. And yes, it's there. And it's also part of physics. There is the edge of what we can see. This is the edge of the visible universe. And there are phenomena beyond that we cannot discuss because we can't see them and they're there. But we can look at early on at the universe, looking very far, we see what the universe looked like long time ago because it took the light from these faraway places long time to reach us. And sooner or later, we will understand better the Big Bang. We'll understand how the universe was created, partly using these ideas from string theory. And this will shed more light on questions in cosmology. Cosmology is a very active field. When I was your age, cosmology was considered fringe science. People had crazy ideas, not measure anything, and so forth. Today, it's a precision science. Not only is there an understanding, there's a standard model of cosmology. People measure things more and more accurately. There are disputes about the next digit of accuracy. There's a model that works, and some of that is being questioned now. This is a very active line of research. Our understanding has progressed tremendously over the last several decades. I believe it will continue to progress because there are new measurements from satellites and other telescopes, other wavelengths, and more data is accumulated, and the picture becomes more and more complete.
Also, it is interesting to know, just to add, that as you said that Big Bang you mentioned. So it's like the two scales, the largest and the smallest ones. They are like playing there's some interplay between these two, right?
That's right. You're completely right about that. But the reason it happened does not contradict what I said about the separation of scales. Because once the universe was very small, it was really physics of short distances. So there's no way we'll understand the Big Bang without understanding microscopic physics. Some aspects of it we can do without. Once the universe was big enough, we can understand how galaxies were formed. But early on, before that, there was inflation and all sorts of other ideas. But as we go shorter and shorter distances, this will connect to that. So when the universe was very young, it will connect to that. And if these ideas are right, we cannot discuss what happens when it was younger than 10 to the minus 43 seconds, because that would be the end, or the beginning, actually.
There's a question up there, and there's one there.
Hello. Sir, you have said that at the Planck scale, there's no concept of space or time. So I just wanted to know, is it right to say that at Planck scale, we can say that the Planck scale is like the space is not continuum, it is discretized, and Planck's scale is the unit of their discretization. Can I
That
say
could be the answer, and it has the right flavor. Imagine space is kind of a lattice, and this is the distance between the lattice points. I believe it will be much more interesting than that. One reason I believe it will be much more interesting, so it fits the description that I was pushing forward, it's kind of discrete. We cannot ask what happens at shorter distances because only these points of the lattice make sense. I believe this will actually not be the right answer. And I believe it for two reasons. First, it's too boring. It should be something much more interesting. But other reason is that in those cases where we know how space emerges, it's far more sophisticated than that. So I don't have a complete answer, but you're on the right track. So there is some granularity. It is as if there is only a lattice, but there will not be a lattice. There will be something much more interesting.
okay?
Okay, I think there's a question
excuse me,
up
sir.
there first. Yeah, I think you can go ahead. Yeah.
Yes, am I audible? Yeah. So my question is regarding like how you drew the conclusion that reductionism ends where like you find that space-time is emergent, because could the world sheet theory not be like a low energy theory of something else, effective low energy theory?
Right. So as we progressed, there was this reductionism of reductionism going outwards, and we go inward to find the more complete theory. And that's how we progressed for centuries. And we still have a long way to go, and there could be lots and lots of layers of new phenomena at shorter and shorter distances. Having said that, once we reach this Planck scale, we know that things will change. Now, we do not know how they will change, but the understanding of string theory that we have today suggests very strongly that we cannot ask what happens at shorter distances. Because whenever we try within string theory to ask this question, the theory tricks us and stops us from addressing this question. In addition to that, there are certain circumstances where we can see that space itself, we can describe all of nature without ever mentioning space, and space appears as an approximation at long distances. Putting all this evidence together, it's reasonable to believe, and all string theories believe that would be the case with space. Time is more questionable, because time is much more confusing. But for space, I think it's quite solid. Now, exactly what will replace it, what will be the true description of nature there, from which space emerges, we don't know. In the example of the water, it would be that instead of talking about the surface of the water, we know that there are molecules there. So we are looking for these molecules. So it was suggested that maybe space is like a bunch of points. That could be the case. Honestly, I believe it will be more interesting.
So
Yeah. Who has the mic there? Okay.
So, um, um, thank you for the talk, sir. And forgive me for my naivety of the question if it's so. So I was trying to follow a line of logic to try to make sense of what could be the possibility for what could be more fundamental than distances, because from a young age we are learning distance is equal to time into velocity and all those things. It's very fundamental. I'm thinking in terms of, let's say, for example, a system of many particles. When I talk about just one particle, I do not have a concept of temperature. But when I take a system of many particles, now I suddenly have the concept of temperature emerging out of it. Now I'm thinking of distance of something as something like that. And a single particle system does not have a temperature, but a many particle system does. So in a similar line, I am thinking, what if the fundamental property is something that's independent of distance and time? And the first property that I have heard of, or at least dealt with in some level, that I could see could be similar is entanglement. So entanglement, I have a feeling that it's irrespective of distances. It's kind of scale independent in my opinion, but I might be wrong. What do you think about that? And could it be the what do you say, the unifying property at both small and huge scales?
Okay, so first of all, the analogy with temperature is excellent. This is another example how we get something that we cannot discuss the temperature of one atom, but we can discuss the temperature of many atoms. So your example is a good example of some notion like that. More generally, all of thermodynamics is like that, not just temperature. Talk about entropy and all these other quantities of thermodynamics are exactly like that. Now, using entanglement and other ideas from information theory, this is a popular line of research today. People think that maybe that would be a way of organizing our thoughts about the fundamental laws. And maybe the fundamental laws will really be formulated using ideas of entanglement and information theory. I do not know whether this is the case or not, but it is one exciting line of research.
Okay, we'll take maybe.
I want to make one more comment about something you said. You said that something is intuitive and something else is not intuitive. We are used to that. People thought that the earth is flat. That looks very intuitive. Now we know it's not, and we got used to it. It's not intuitive that the earth is round, but we got used to it, and now it's more or less intuitive to us. And there are many other things like that in science, that in everyday life it looks one way, but once we go to longer distances or shorter distances, it looks completely different. So I think that's another example of our view being changed. There was a question here.
Hello, sir.
Yeah.
Yeah.
Oh, here. To your left.
Ah, this is my right, actually, not my
Hello,
left.
I had
Yeah.
nice time listening to you.
Thank you.
I have two questions to ask you. The first one being, I want to know what electrons are composed of. And second one being, you mentioned that both space and time are not fundamental. So what else is fundamental?
Okay, so as far as we know today, the electrons are fundamental. They are not made out of anything. And this is something that can be made very quantitative. If we look at it with this microscope, as far as we can see, as we go deeper and deeper, it's like a point-like object. That could change. It could change that tomorrow, or maybe in a year or 100 years, people will go to shorter distances and the electron will turn out to be composed of something else. That could very well be the case. At the moment, we have no evidence for that. Now, what would be fundamental? That was your second question. There will be some laws of nature, and just as we had that in all the previous layers, the previous laws were replaced by more fundamental laws, and the old laws are derived from it. The same thing will be there. Unfortunately, I do not know what these new laws will be. Maybe if there's a public talk here next year, somebody will come here to give you the answer.
Thank you, sir.
Okay. I'll just ask one question from the online. There are people watching this online on YouTube. So it says, this is Matt who is asking, there are many experiments we have that imply non-locality. I'm not sure what he's referring to, but he says we usually stick to locality in relativistic quantum field theory. How would it turn out if there was no locality in physics? Will it be a disaster?
Well, it's a very good question. Locality is the fact that we cannot influence things as a distance. It takes time. If I want to hit him, it will take me some time to get there. This is the notion of locality. And locality is fundamental in physics. It's closely related to the idea of causality that I mentioned earlier, that the cause is before the effect. It's built into our understanding of physics. What will happen to all of that if space is emergent is a very, very interesting question. And I think it's fair to say that we don't know. We don't even fully understand that in those situations where we understand how space emerges. Even there, it's not quite clear how locality comes about. And with that, I mean not locality in general, but locality on very, very short distances. So it's not completely understood there. Yeah, this is an ongoing subject for research, and there's progress, but we're not there yet.
Okay, I think we'll just take one last question.
I have a question. Last question.
Oh,
I'm sorry, I was waiting from that.
okay.
Yeah. I have a very primitive question. From where does the exponent come from for the Planck's length, 10 raised to power minus 35? When you reach that level, nothing makes sense. What about 10 raised to power minus 34? So from where does
Well, 10 to the minus 34 is larger distances. So you could ask, my main point was about 10 to the minus 36, so that would not make sense. So what Mr. Planck did was to take the fundamental laws of nature at the time he understood. He introduced what is known as Planck's scale, which was the scale, which he didn't know it at the time. This is the characteristic scale where quantum mechanics kicks in. And at the time, the other numbers he knew at the time was Newton's constant, which measures the strength of gravity, and the speed of light. And what he said was, these are clearly basic quantities in physics. So we should use measures in units where these are 1. So the measures that the units that we measure are completely accidental. I think the meter that we use for distances was the distance from the nose of a king to the end of his finger or something like that. Then there's a more modern version of it associated with some quantities of the Earth, some distance between longitudes and something. So all of them are kind of artificial things, unnatural things that people invented. So Planck wanted to find units which are natural to physics. Your microphone is on. So he wanted units that are natural in physics. So he said, the speed of light is very natural. So let's measure velocities in terms of the speed of light. And similarly for the other things. And then it convert these units to the units of length that we do know about. So that's the calculation he did. And when he did this calculation, he found 10 to the minus 35. And he was brilliant enough to say, this is the fundamental physics, length of physics, because this is the length scale that would be kind of 1 if we set all the others to 1. So if we wanted to measure length in fundamental units, that would be it.
Yes, thank you, sir.
I think we can just take one last question. I'm sorry.
Am I audible? Yeah, good evening, Professor. Thank you for the beautiful lecture. I had a great evening. So we mentioned how to get the final picture, we need to capture what happens at 10 power minus 43, right? And experimentally, we've been able to figure out what roughly happens at 10 power minus 18 and before that 10 power minus 15. And the effort that it took to go from minus 15 to 18 was pretty high. And I can't imagine what it would take to go from minus 18 to minus 43. So my question is, if time truly doesn't exist under 10 power minus 43, will we ever be able to capture the property of what happens in that time experimentally? And my second question is, forgive me if this is quite naive because I'm very new to the world of academia. If you can't experimentally verify these processes, which happens in this time scale, will the community ever accept it truly? So,
Okay, these are fantastic questions. And these are fantastic questions, but I think researchers are very imaginative and they come up with great ideas. And a lot of problems that people say, oh, we'll never get there, we'll never understood them, we'll never understand these issues. Somebody bright came along and found a way to do it. And the history is full of such things, history of science. Now, where will it come? I do not know, but it could be that something in astrophysics, you will see something, some faraway phenomenon, there would be something unusual, and people say, that's connected to that. And maybe it will take a long time. Now, we as humans, our time scale, that's not fundamental in the universe. That we live, say, several tens of, few tens to 100 years, that's the time scale. On this planet called the Earth, around the sun, it's a point in the universe. That's not the right time scale. So if it takes 1,000 years or maybe 100,000 years, that could be it. It could also be that there is an intelligent civilization elsewhere in the galaxy, and their brains are much smarter than ours, and they already know the answer. We are not part of the equation. What we are trying to do is try and do our best to find the answer. And we keep making progress, and as long as we keep making progress, I think we should continue doing it.
On that cosmic note, I think it's a good time to end this session. I'm sorry I couldn't take everyone's questions, but I'd like to thank Nati again for the lecture with a small memento from ICTS. And this is an ICTS water bottle, which I think you'll find it hopefully something that you can carry around. And there will be a hoodie also, which will be, I think, which is not here, but which will be sent over to you. So anyway, thanks Nati again for a wonderful lecture.
Thank you.
And for entertaining all the questions.